It's almost time.
Actually, it is time. So any set of functions, f1, f2, up to fn, is linearly independent if the only constants, c1, c2, blah, 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 that make this linear combination of those functions equal to 0 would be all the c sub I equal to 0. And in other words, one of these can't be made with some linear combination of the other ones. That's really what it boils down to. I hope that's understandable.
I want to discuss all this behavior.
Well, I mean, the behavior is, if f1, for instance, is, you can make f1 by negative this one plus negative this one, then they're not linearly independent. So, any set of functions like this is linearly independent if there exists, or sorry, linearly dependent, bad word there, if there exist constants, not all zeros, such that this is equal to 0. That means one of them, at least one of them, is a linear combination of some of the other ones. In general, linear dependence means one function is a linear combination of the others. That's it. Linear independence means no function is a linear combination of the others. So let's look at some examples.
Okay.
All right, so here's example 5, 6, and 7. The functions y equals sine of x times cosine of x and y equals sine of 2x are dependent. And so I would like to ask the question, why?
Oh.
Well, there's a reason why I would like to ask the question, why.
I'm sorry, I can't.
Well, you don't have to, but can you explain to me why they're dependent?
I'm so ready.
Well, I'm glad you're ready, but now, can you explain why this one, this function, and this function are dependent? And the answer is, you can make this function because it's really just 1/2 of this one. I would ask you to recall the trig identity that says sine of 2x equals 2 sine of x cosine x. Well, there is half of 2 sine of x cosine of x. So therefore 1 is really just like a multiple of the other one. Well, we only had 2, and if one of them's a multiple of the other, they're not independent. They must be dependent. Okay, I hope that's clear.
That's the loveliest thing I've ever heard.
Well, great, great, great. Now, the functions y equals x and y equals x squared are linearly independent because you can't really make, I mean, you can't take x and multiply it by a constant and get x squared, and you can't take x squared and multiply it by a constant and get x. So they're obviously linearly independent. Well, yeah, I guess it's obvious. I hope that's obvious.
That's okay. That's okay.
Well, good, good. I'm glad that's obvious. So, these three functions, cosine squared of x, by the way, this is the way I have to type cosine squared. My software won't like cosine and put a little 2 in here. G of x equals sine squared of x and h of x equals 1 are linearly dependent. So, can you think of a reason why they would be linearly dependent?
I've been doing a lot of thinking.
I would expect you would be doing a lot of thinking. Why do you think they would be linearly dependent?
I'm sorry, I can't.
Oh, come on. Think just a little bit harder. Just a little bit harder. Just a tiny bit harder.
I don't understand.
Well, okay, I'll tell you what. Think of a trigonometric identity.
I can't take this!
Well, just bear with it and think a little bit harder about a trig identity.
Oh, yeah?
Yeah. So here's what you want to do. Look, cosine squared plus sine squared equals 1. Duh. So h, the function h, is just a linear combination of f and g. Therefore, they are dependent. But that does raise a question, as you know, I mean, I was able to luck into these three, but it might not always be so nice. So let's try to think of another way that we can determine if functions are linearly independent or not.
I'm so ready.
Great. It'll be in the next video.